So in the last class, we discussed about how we can analyze the stability of a slope when it is subjected to earthquake motion. So basically, we do the pseudostatic method of analysis, and we have understood that whatever analysis that has been developed, the pseudostatic method which has been developed for analyzing the stability of slope subjected to earthquake forces is basically it is developed around the limit equilibrium method, right? So limit equilibrium method. And all the shortcomings of this method is also inherently taken up by the pseudostatic method of analysis. So definitely what it does, so limit equilibrium method, so pseudostatic analysis, so based on, so pseudostatic analysis or method of analysis, it is based on limit equilibrium method, and what it gives is basically the factor of safety of the slope. So only the factor of safety. So it is almost like an index of the stability of the slope. So it assumes a slip surface. So it is assumed that the soil will fail, the mass will fail through that slip surface, and what are the stabilizing forces and moments, and what are the destabilizing forces and moments are calculated, and the ratio of that is the basically the factor of safety. So it does not give anything, any information regarding what will be the deformation in the dam or in the slope. So regarding the serviceability of a dam, so suppose if we consider the serviceability of a dam, it is definitely, it is controlled by the deformation. If the dam or if a slope is significantly deformed, definitely it will be rendered useless. Alright, so especially after an earthquake, there, as we have seen, there may be significant amount of displacement in the slope induced, and therefore to assess the serviceability of the dam, we have to be able to assess what may be the deformation, the total deformation after an earthquake occurs, after an earthquake affects the particular dam. So for that, we have seen that we have developed various deformation analysis. So we have discussed the Newmark's method. So as in limit equilibrium method, so we assess the total inertial forces, so whether it is static or whether it is dynamic. So static is the W, so due to the gravitational pull, so that is the inertial force on the mass, sliding mass. And if there is dynamic force, so we assume that there is a acceleration in the horizontal direction. So that is the dynamic inertial force that we assume that will occur on the soil due to an earthquake. And of course, that total destabilizing force or moment we divide it by the available resisting forces, all right, or the soil resistance. And also we have seen that limit equilibrium method, it cannot take into account the variation in the soil resistance due to various earthquake loading. So we know that the stiffness, so if this is G, we have seen that the stiffness varies with the strain. So larger the strain, the stiffness reduces. So with reducing stiffness, definitely the deformation will increase. So then there may be flow kind of failure, liquefaction. So all of those factors, limit equilibrium method, they cannot handle. Now Newmark's method is also based on the inertial forces. All right. So we equate the inertial forces, and we find out what is the minimum, or the minimum threshold that will be required to cause the displacement in the sliding block. So in that case, if we consider this to the limit equilibrium method, so it is basically the factor of safety becoming less than 1. Alright, so when the factor of safety becomes less than 1, the block will move, the block will slide. Alright, and as soon as again the factor of safety increases, alright, so there is reduction in the acceleration, so the factor of safety increases, the block will again stop. So stopping moving, that is what Newmark method is basically doing. So that is the analogy of the sliding mass. So we have a sliding failure, and that it is considered to be analogous to a sliding block. Right, so that is the Newmark's method that we discussed. So we have already discussed the various forces acting on that and how we develop the yield coefficient of horizontal acceleration, all right, or pseudostatic coefficient, horizontal pseudostatic coefficient, and we see that when the factor of safety is almost equal to 1, we can consider that the block will slide, and based on that we find out what is the ky. Alright, so ky is the yield pseudostatic coefficient, so the acceleration ay is given by ky into g, so that is the yield acceleration. Alright, and ky is equal to tan phi minus beta. Alright, so when kh is greater than ky, so there will be sliding. So in case of limit equilibrium method, so LEM, if we do the analysis, so factor of safety it will show less than 1. So there will be sliding. As soon as the KH reduces below KY, so it goes below KY, so the block will stop. So that is what we have discussed. Okay, so we have seen that if this value AY, which is equal to KY into G, so if the acceleration in the mass exceeds beyond this value, so that acceleration will cause a velocity development in the in the block. So the block will start to move. So at what rate? So if we integrate acceleration into time, all right. So that is the acceleration into time. So that is the velocity increment. So this will increase up to this value over here. And then as soon as the acceleration will again drop below the yield acceleration, it will stop, and the acceleration it will stop, but the velocity it has increased from here, so it will again decrease up to 0, considering on the frictional force that is being applied. So the block moves for this much of time, alright, with a velocity increasing and decreasing. So if we multiply this, that means if we find out the area of this, we will get the displacement. So here is the maximum velocity, therefore the displacement rate of displacement is the maximum, the slope is maximum, alright, then it decreases, so the slope decreases and ultimately stable stops. Okay, so from here to here it increases, so the rate of displacement increases. Again from here to here it decreases, so the rate of displacement decreases. So ultimately what Newmark did was, so he found out what is the Newmark, what he did, Newmark found out the displacement which may occur. Alright, the total displacement, not this area, of course. So the total displacement which may occur. So this displacement which has occurred. So for this particular time step, the displacement which has occurred, so we can find out as this one. So T1 is the interval, T0 to T1, this is the interval, time interval. So the del relative means relative to this slope. Alright, so the block motion or displacement of this block relative to this plane, alright, or actually relative to this stable mass, alright, the displacement of this sliding block. So that is given by half of A minus A1. So this is the region into delta T square. AY minus A is applied for this much of time. Okay, this much of time. So A minus AY, so this is the acceleration that will cause the displacement. So that is applied for this much of time. So this is delta T, sorry, okay, so this is delta T. So A minus AY, so A minus AY into delta T, alright, so that is the velocity increment. Okay, so that is the velocity increment. You see A into delta T. So this is increment in the velocity. Then we have to find out the area. Alright, so half into A, that is actually this is A minus AY, sorry, again. This will be A minus AY, this one. Okay, so A minus AY into delta T into delta T. Okay, so this is this value over here. Okay, so that is the additional displacement that we have. Okay, so that is how it is integrated. So this concept is easy, but thing is that similarly each time step, so we have to sum up. So here ultimately we find out what is the area. So this is the area, so this is the velocity, this is the velocity increment. Okay, and then this is the remaining, the gradual stoppage of the sliding block. So we have a total displacement of this much. This is the total displacement for this peak. Okay, similarly here we have this much of increment in the velocity, and then there is a reduction in the velocity. So total area, so we have from here we have this much of increment up to this one. Okay, so basically what we can do is we can sum up the distances over when there is an increase in the acceleration more than the yield acceleration. Okay, so that is what Newmark did. Integrated. So another way of saying integration is the summation. So we can also sum up the distances for the increment in the peak acceleration. All right. So then we find out what is the maximum relative displacement. Okay, so we see that the relative displacement of the sliding block, it is ultimately dependent on this coefficient, that is the yield acceleration basically. So if the yield acceleration is more than the Amax, so this is Amax. If yield acceleration is above Amax, so definitely no deformation. Okay, and if it drops below Amax, so here we see, so based on the shear strength of the soil or shear resistance of the soil, so we will define the AY, and here we have only this much of displacement, this much of exceedance in the acceleration, and therefore we can integrate this, we can get the velocity, after getting the velocity curve, integrate that, we can get the time displacement curve, and we can find out what is the displacement. So definitely if AY is further reduced, so we can see that there will be significant amount of displacement. Okay, so Newmark in 1965, so Newmark in 1965, so he obtained, so related to one single pulse of the on the slope. All right, so single pulse on the slope related to a single pulse. So here one pulse. All right, so this is one pulse. So like that. So say it's related to a single pulse. So displacement in the slope he gave by this equation. All right, so where Vmax is the velocity, maximum velocity at the base of the slope. All right, so at the base of the slope over here. All right, so Vmax, whatever is here, so the maximum velocity is the Vmax. All right, so at the base of the slope. So based on that, he gave Newmark 1965 gave a relation to obtain the displacement considering one single pulse. That means only one pulse. Right, so we have to again sum up the uh, distances over if there is further accidents of the yield acceleration. All right, so as we know, so Vmax, it can be related to A into delta t. All right, so delta t is the time by what amount the acceleration has exceeded. So this is the A delta t over here. Okay, as we have discussed. So Vmax is the maximum velocity there achieved. So he gave after analysis of several earthquake, so that he proposed, Newmark 1965 proposed, after analysis of several earthquake, Newmark 1965 proposed that we can modify this equation to this one. So the maximum displacement in a slope that can occur due to an earthquake is given by this equation. Okay, so this is given by Newmark in 1965. So based on this concept, okay, based on this concept. Then, so here what we have considered is, we have considered only the force equilibrium. So here you see, we have considered only the force equilibrium. So all the forces are summed up, and stabilizing force by destabilizing force, stabilizing force by destabilizing force, static case, dynamic case. Okay. So Newmark 1965 also gave similarly for concept for moment, considering the moment in the slope. Okay, so as we know, factor of safety is equal to stabilizing moment by destabilizing moment. Okay, so here, so first of all, let us consider on the stabilizing moment. So stabilizing moment, here it is considered only, so the slope is considered to, the total shear, strength parameter of the soil is considered. So we have C, okay, we have C and we have the unit weight. Okay, so here what is done is, so we divide the slope into equal numbers of sections here. All right, so if I multiply that, so if this is suppose ds, okay, so ds, so tau s into ds, we can say that. All right, and then we sum up. All right, so the moment for this one will be r tau s ds. Okay, so we have the factor of safety is equal to stabilizing moment by destabilizing moment. Okay, and we divide the arc of the slip surface into numbers of equal division. So let us say that this is ds, the length of this arc. So if the shear strength here is tau s, so tau s into ds is the total shear strength here in this direction. Okay, if I multiply this with the r, so I get the moment. So if I summing up r into tau s into ds, I will get the total stabilizing moment, as we have discussed in the moment equilibrium method. Okay, so r we can take out. So we have the total stabilizing moment ds. Now problem is that in case of earthquake also, this will remain same. Okay, so in case of static condition, so we have this weight w. So this is the weight w of this mass. So weight w into this lever arm b, suppose we consider this lever arm b. So weight into b is the destabilizing moment. Okay, so we have r summation tau s ds by wb. So this is the factor of safety in case of static condition. Alright, so no earthquake forces. Now in case of earthquake force, in a case of pseudostatic analysis again, so what is considered is that, so alpha psi is considered. So alpha psi, where this is alpha h and this is alpha v. Okay, and this is angle psi. So the resultant is considered in this direction. So this is an additional force due to the earthquake. Inertial force, additional inertial force due to the earthquake. So in this case now, what will happen is that, so we already have WB. So we already have W into B, destabilizing moment. Apart from that, we have this alpha psi into W. So that this is the force and this is the lever arm H. So about this H, so it is rotating in this manner. Okay, so that is another moment. So now the factor of safety will be given by, again same, it will remain, stabilizing moment will remain same, tau s ds, but you can see here it has increased. Okay, so ultimately in this case also we can find out what is the yield acceleration that is required. Alright, so the yield acceleration in this case is given by, so ay is given by factor of safety in static case minus 1, so b by h into z. Alright, so in this case we can, just as here we have expressed the ay. Alright, so this is ay, which is equal to ky into g. Alright, ky is tan of phi minus beta, so it is very simple in this case. In this case also, here we can express it as ay is equal to fs minus 1 b by h into z. Ultimately this, now this ay will be used in this concept, and we will find out the what is the relative displacement of the slope. Okay, so Goodman and Seed in 1966. Okay, so Goodman and Seed in 1966. Okay, so they solved this system, this concept, they solved this concept for frequency of 1 hertz or 1 cycle per second, we can say. Alright, 1 cycle per second or 1 hertz, you can say. So they solved this system, and for a sinusoidal time history. So as you have seen here, so earthquake time history. This is acceleration with time. All right. So this is acceleration with time. Here we have considered a rectangular waveform. All right, of acceleration versus time. So this is a rectangular. So sinusoidal will be when the acceleration will increase and decrease as a sine curve. All right. So using that assumption, considering sinusoidal acceleration time history and frequency of 1 cycle per second, okay, they solved the system, and what they gave is the maximum acceleration coefficient, all right, versus the displacement. So this is the displacement in mm. All right. So this is the plastic deformation. So this is the plastic deformation. That means the deformation which cannot be again regained. All right. So that is the plastic deformation in mm, right, in millimeters. Okay. So that is for 1 cycle per second, and for considering sinusoidal acceleration time history. Now displacement per cycle. So this is per cycle. So if if the frequency content is different, suppose we have 2 cycles per second. So what we can do is, so for in that case, so if we want to find out the displacement, so suppose d for this 2 cycles per second. So what we have to do is, so the values from here, all right. So we have to divide it by the frequency, all right, frequency square. So then we will get the displacement. So this is displacement for 1 cycle per second. So from here we have taken, so for phi equivalent, and this is another normalized angle of internal friction. So we will see how we can use that. So for 1 cycle per second, whatever displacement we have, we divide it by the frequency that we have in our hand. So 2 cycles per second. All right. Square that, and we get the displacement per we get the displacement for that corresponding frequency, all right, for 1 cycle, of course. So if there are suppose n numbers of cycle in the earthquake, so as we have discussed, so 6.5 have maybe 10 numbers of cycle, then 8.5 have 30 numbers of cycle, as we have discussed. So in that case we have to multiply that with the numbers of cycle. So then we will get the total displacement. Okay, total displacement. Of course, it has to exceed this acceleration. Okay, so the total numbers of cycle which exceeds this acceleration, maximum acceleration coefficient, so those only we have to add it. Okay, so that that part we have to keep in mind. Then again, so here we can see the slopes are given for, values are given for some particular slopes. So what we can do is, so suppose the slope is 2 degree or 4 degree flatter than this. So the slope is 4 degree flatter than this. So what we will do, so instead of 54 degree, we will use the 50 degree curve to obtain the acceleration, or to obtain the maximum displacement. Okay, so we have the coefficient, so we have this, suppose, so there is no, so here we can see, so here it is 150 mm, right? So we will increase, so if the slope angle decreases, so we will increase the angle of internal friction. So 46 means if for this slope we have phi equivalent of 46 degree, so for a 40 degree slope flatter than this slope, we will have 50 degree. If the slope increases, then we will use, so in this case it will decrease, the phi equivalent will decrease. So in that case, like that, we will obtain the maximum acceleration coefficients, and the plastic deformation that may occur in mm. Okay, then again, Yejian et al. In 1999. So Yejian et al. In 1999. So what they did is they obtained normalized displacement, permanent displacement of for AY by Amax, okay, for different earthquake time histories. So this is rectangular, so rectangular time histories. So we have, so this is suppose AY and we have this exceedance here. So this is sinusoidal. So as we have discussed, sinusoidal, okay, and this is triangular, like this. So we have this exceedance here. All right. So uphill this displacements are mostly ignored. So downhill displacements are only considered. So ultimately, they have obtained a normalized curve, right, for different AY by Amax values and the normalized displacement. Right. So normalization is done considering to peak acceleration of 0.5 g. All right. So 0.5 g normal. They have considered for finding out this displacement, and the peak velocities they have considered is 76 centimeter per second. Okay. So that is they have considered. So using that we can find out what is the displacement in a slide, and the concept is same. All right. So they have used this Newmark concept to find out this equations. Okay, so ultimately and also they have for suppose equivalent numbers of cycles. So what is the accidents, probability of accidents? So equivalent numbers of cycles means number of cycles where their yield acceleration will increase. So in this case it is only for one cycle again. All right, so these are all for one cycle. So if it exceeds for 2-3 cycles, so number of how many numbers of equivalent cycles are there? All right, and obviously the earthquake, what is the predominant period of the earthquake? So based on that, what is the probability of accidents? So here you see, so from 1 it goes on increasing in this manner. Okay, so this is the AY by Amax and this is the displacement. So then using the same concept, using this concept again, so Bazier et al. Bazier et al. So Bazier et al. 1992. So they gave an expression for the displacement considering equivalent numbers of cycle in the expression itself. So here n is the equivalent numbers of cycle. All right, and then they define the function for f of a by ay by amax. So ay is the yield acceleration, amax is the maximum acceleration. So the function actually they derived using the calibration, using various case histories. All right, so this is basically an empirical calibration. So they used the data from various case histories and they assumed harmonic accelerations. All right, so as we have seen in earthquake, it is random. All right, but In the analysis, they compared that with harmonic motions. All right, and then they gave a function of f ay by amax for various ay by amax. All right, and this is the function. So based on that, they obtain this equation for the displacement of a slope. All right, and then they compare that with the method given by Youd and Perkins in 1987. So Youd and Perkins, what they did was they obtained the relation using the LSI here. All right, so LSI, it stands for liquefaction severity index. Okay, and for various indexes, so from various based on observed lateral displacements, basically case histories again. So case histories, basically case histories again. So based on the lateral displacements which have been observed, and most of the case histories they considered were of lateral spreads. All right, so lateral spreads they considered. So on floodplains, okay. So on floodplains, what is the displacement? Is what they considered for gently sloping, mostly gently sloping grounds, and they considered that on fluvial deposits. All right. So we see that for various magnitudes, they gave what may be the liquefaction severity index. All right, and then they gave also a chart where they have described what may be the ground condition, right? So for various liquefaction severity index, all right. So we can say that if it is 90, so there will be very abundant ground effects, including numerous sand boils, large aprons, all right. The cracks, that means 30% or more of some areas covered with freshly deposited sand, many long fissures, all right. So like that, various conditions they have given what may occur in situ in the field, and they use this concept to produce probabilistic LSI maps, all right, mainly Southern California. So they have given that, and it was seen that the method given by Bajier et al. 1992, it compared well with the LSI method. All right, so here we see that it compared the horizontal displacement. It compared well with the two methods. All right, so it compared well. So various magnitudes of earthquake they have considered, and we can find out what is the maximum displacement. Okay, so then Bartlett and Youd, all right. So Bartlett and Youd again, they considered various case histories. So they use a large database of again lateral spreading, all right, and again they have used the lateral spreading case histories, lateral spread case histories, all right, and then they use the regression analysis. They used the regression analysis, and then they gave two equations. So this first equation is basically for this free face model which they have described. Alright, so this is the free face model which they have described. So here if you see, MW is the magnitude of the earthquake, R is the horizontal distance from the seismic source. Alright, so R is the horizontal distance from the seismic source. Then W is what they have defined as free phase ratio. Alright, so W is the free phase ratio, which is L by H by L into 100. Okay, and T15 is basically the cumulative thickness of the layers. So if suppose this slope, if this slope is composed of layers like this, so suppose this layer has an n corrected value of greater than 15. So this thickness of this layer will not be considered. And if these two layers have n corrected value less than 15, so this thickness plus this thickness, okay, that is T15. Okay, cumulative thickness of the saturated, and of course it has to be saturated, all right, and granular layer, all right, granular layer, and the n value, corrected n value, has to be less than 15. So we add up wherever n value is less than 15, we add up the thickness of those layers. So that is T15. Okay, and F15 is the average fine contents of these layers which are added up. All right, so if this is suppose 6%, 5%, and if this is suppose 6%, so 5 plus 6, so 5.5% is the value that we'll be using here. And D50 is the mean diameter of the particles of these layers, whichever is added for to obtain this T15. Okay, so here we obtain the displacement. This is the displacement for the free phase model, and this is for gently facing, gently sloping ground. Okay, this is a gently sloping ground. So two models they are given. So these are all empirical equations, as I have told here. So based on regression analysis of significant numbers of lateral spread case histories. Okay, so that is what they have developed. And one thing that I wanted to show you here was, so here you see, so using that particular equation, so the displacement of this slope was calculated. Okay, so this slope was calculated, and you can see for magnitude of 6.5, only 6.1 centimeter of displacement occurred. Okay, but if you see for magnitude of 7.5, 91 centimeter of displacement occurred. Okay, so it is almost like, if we correlate that with the this one, the Newmark analysis and the various studies that have followed, all right, by Jed et al. And Uden, Perkins, and all those things, all right, and then Eugene et al. 1999, Goodman and Seed, all right. So if we compare that with that, so we can consider that in M magnitude of 6.5, the acceleration, maximum acceleration, was significantly lower than what it was in 7.5, and obviously in 7.5 magnitude also the number of equivalent cycles will also be more. All right, so there is, you can see a significant amount of displacement. All right, so this earthquake may have caused failure in the dam. Okay, so that idea we have to inculcate in our, we have to visualize that. Okay, so this is regarding the use of Newmark's concept, and we have developed various models. Then again, now if we consider a slope, all right, the displacement in the slope when there is high frequency short wavelength content, so we can see that there is different mode of motion in the same slope, right, compared to the low frequency long wavelength. So most of the earthquakes are actually of this short, of this range only, so it is of low frequency. So we have this entire mass sliding, all right, and obviously apart from that we have different behaviors of soil. So we have rigid So this is of course rigid, and this is considered strain softening. So the with strain, the stiffness of the soil reduces. So most of the soils are of this sort only, where we see that the stiffness of the soil decreases with increasing strain. And this is of course rigid perfectly plastic, that what has been considered in the Newmark analysis. That is what has been considered, but actually it is rigid and strain softening. Like that, mostly it is like this. Okay, so it is mostly strain softening. And of course, in some cases, there may be strain hardening as well, where there is dilation in the soil, all right, and there is negative pore pressure generation. So in that case, there may be strain hardening as well when there is a dense soil. So we have to take into consideration all of that fact. So Maxide and Seed in 1978, all right, they so so in 1978. So they consider the dynamic yield strength to be 80% of the undrained shear strength, and that is what they defined. That is what they used to define the yield acceleration. Okay, and then they said that within a slope, the A max at z equal to 0, that is here. All right, so it varies with depth. Okay, so Mx average by Mx z, it varies with depth. So they did FE method, analysis, finite element analysis, and shear slice ranges from various data. All right, and then they came out with this particular curve. So this is the range of all available data that they have collected. Okay, and then they said that with variation in the depth, so z by h, with variation in the depth, so this is z increasing, increasing, and increasing. So we have this z by h. We have a change in the acceleration within the soil mass. All right. So and the acceleration, that is how it changes. Okay. And then they collected. So what they did, they plotted the variation of the average maximum acceleration with depth. All right. So this is the plot of the variation of the average maximum acceleration with depth, and this is what they got. And they showed that the acceleration is not constant within the embankment. Okay. And for various case histories, they summed up the displacement and they normalized it. All right, so A max into T naught. So T naught is the equivalent time period of the earthquake, and A max is the this maximum acceleration. So they normalize this as a ratio here, and for different yield acceleration and A max. All right, and then they plotted from various case histories that they have recorded. All right, and they saw that it all falls within this range. So this is the range it all falls within. Okay, if they plot it like that. So ultimately they gave for various earthquake magnitudes. So for various earthquake magnitudes, they gave the displacement by A max T naught ratio to the AY by A max. Okay, so if we know AY by A max, we find out here, so what is the magnitude of earthquake, and from here we find out this ratio. So the maximum displacement in the this slope will be given by this ratio into A max by A max into T naught. Okay, so easily we can obtain what is the maximum displacement. So ultimately it is seen that observation is critical in case of obtaining the maximum displacement what can occur in field due to various earthquake motion. All right, and we have seen that we need to consider the displacement when we are analyzing seismic stability, or when we are analyzing the slopes, especially for serviceability of the slopes. All right, so that is a very important conditions we need to take care of. Now then again, so up till now what we have discussed is where the soil is consistent, the shear strength of the soil is consistent, all right, and there is no chances of liquefaction. So Lucia et al. 1981, they gave this deformation analysis, so flow failure deformation analysis, so based on if there is a slope which may undergo flow failure. So they assume the slope to be of this volume, all right, and after a flow, same volume will be preserved, and only the thing is that it will be spread out. And this is the critical height which they have defined, and this is the ht at the end of flow. So what they have done is, so they have plotted two curves. One is for the volume and one is for the strength. So this is the volume curve and this is the strength curve. Alright, and for various angles of beta, alright, they have obtained what is the n naught, alright, and what is the slope angle alpha after the failure. Alright, so alpha after the failure, that is after the failure. Okay, and then they have given various slope angles here. Alright, so and then the slope angle alpha here. So based on that, we can obtain initially, so this is the volume. So we have this volume over here. So this is A1, A2, A3 and HC. HC is, and then from there, after flow failure is has occurred, so it will flow up to this point. But the thing is that the volume will remain same. They have what is that they have assumed. All right, so the volume of the flow will remain same. HT and alpha stable is obtained for this volume curve. Beta here, so this is the slope angle beta. So slope angle is beta. All right, and then alpha is what is after the failure. What is the slope angle alpha? All right, unit weight. Okay, and then n naught we obtain from this curve over here. So once this h stable and alpha stable is obtained, we obtain what is the length of the flow failure. All right, and then tan alpha stable. All right, alpha stable is what we have obtained from here. ht stable we have obtained here. Equation n naught we have obtained from this curve over here. All right, and then we can obtain hts. So from there we can find out what is the length of the flow of the slope. Apart from that, we have already discussed how we can use the Taylor's method, modified by Prakash, Sharan and Raj. So we can obtain, so here what are the things that we need is the cohesion C. Alright, we need the cohesion C, we need the angle of internal friction phi, we need the angle of slope beta, okay, and then we need what is the height of the slope h, and then we need what is the unit weight of the slope. Right, so from there we can obtain first of all this modified stability number. From the modified stability number for various alpha h, alright, for various alpha h and for various slope angle beta, we can obtain what is the modified factor of safety on strength. Alright, so from there again, if we multiply that with tan phi dash, so fs we obtain, so fs equal to f star into tan of phi. Okay, so easily we can do. Okay, so we have seen that there are various methods of analysis of slopes. So obviously we can divide that into two. One is the limit equilibrium method where we get the factor of safety, and one is the deformation analysis where we get the deformation of the slope. All right, so deformation of the slope is also important, and as far as the serviceability, and we have seen that if there is significant amount of deformation in the slope, it may lead to cracks and fissures in the slope, and water will seep in, all right, and there will be, what will follow is catastrophic failure. Okay, so thing is that we need to assess every possible angle, and we need to converge into a solution. Okay, so that is the slope stability analysis. Of course, uh, slope stability analysis, what we have discussed here, is very basic and very, in a very, what to say, like in a just a introduction is given. Okay, so now slope stability analysis has, evolved in a lot, in a considerable manner. All right, so there are lots of different, models for analyzing flow failure. All right, so there is runout models where we can, assess the runout of the slope. All right, then there are limit equilibrium methods. Then there are finite element methods. So for slope stability analysis, that is when we consider the factor of safety, we have the limit equilibrium method. All right, so limit equilibrium method also we have discussed that we have various methods. All right, starting from the Frobenius, which is the most simplest manner. Then we have the Bischoff's, Spencer's, all right, and various other. Then most rigorous one is the Morgenstern price. All right, and basic advantage of LEM is that we can include lot many, like pore water pressure we can include there, submergence effect, drawdown effect, all right, all those can be easily analyzed. Apart from that, earthquake effect, all right, we can easily include that. So that is one of the advantages of slope stability. Apart from that, for slope stability analysis, we have the strain stress deformation analysis. All right, so FEM we can use for that purpose, finite element method. Then we have the discrete element method. All right, in fact FDM also we can use, so finite difference method also we can use, so using the Lagrangian, this calculation. Then we have the discrete element method, DEM. All right, discrete element method, where the slope is divided into discrete elements. Okay, into discrete elements in this sort. All right, so discrete elements. So then there are runout models. So there is smoothed particle hydrodynamics model. All right, SPH, smoothed particle hydrodynamics. So it models the runout of the soil. All right. So if time permits, I will show a slide of the latest advancements in slope stability analysis, and of course also in this runout modeling of debris. Okay. So whatever we have discussed here is very preliminary and very, it is just for an introduction and to understand the basic concepts of the things. Things have evolved from what I've discussed as of now. All right, and we need to keep up to date also, if definitely if you want to go into research into this line. All right, so we will stop here. Okay, so we will stop here. And here you see, we can see there are a lot many landslides. So here there is a landslide occurring. So here you see these are all in Arunachal. All right, so you can see this is a landslide over here. Okay, so this is a landslide over here. So you can see how the debris has run out. Okay, it has run out like this. Okay, then yeah, there is a huge landslide here. Okay, so here you can see. Okay, so a huge landslide there. Okay, and the debris, it has run out all to the river. All right, to the river it has run out. Okay, so various models are there to assess and evaluate all this. So here you can see. So here you can see there is a landslide here. All right, there is a landslide here, and it has all the way, the debris has run out all the way, and here up to the river. Okay, so there are a lot many landslides. All of these are in Arunachal Pradesh. All right, so Mebo region. All right, so here Pasighat, near Pasighat. Okay, that is where it is occurring there. All right, so you can check various conditions prevailing there. All right, so a lot of landslides are there, small landslides as well. Okay, small landslides as well. So here you see a small landslide. So that is what we have discussed as of now. So this will summarize the chapter. All right, and in the next class we will continue with the other chapters. Okay. Okay, thank you.